If I say a sentence like, I grew up in France, I speak fluent blank, you already know the missing word is French. To do that, your brain had to carry information forward through time and keep it available until the moment it became useful. That is the basic problem of sequence learning, where information unfolds step by step, but what matters now may depend on something that happened much earlier. In this case, filling in the blank depends on the earlier context, grew up in France. And for us humans, this feels effortless. But for early neural networks, this was extremely difficult. Earlier in the series, with Hopfield networks, we already saw neural networks are capable of storing patterns or memories. But sequence learning requires something more specific. Not just storing information, but selectively storing information, and relating that information through time. In other words, learning long-term dependencies. Early neural nets could in principle represent these dependencies, but training them to reliably learn over long timescales was very unstable. Today's video is about the architectural response to this kind of problem. Welcome to the third video in my AI architecture series. We'll be discussing the architecture of LSTMs, or long short-term memory, introduced in a paper by Sepp Hochreiter and Jürgen Schmidhuber in 1997. So far in the series, we've covered memory and recall with Hopfield networks and semantic structure with distributed representations. Sequence learning brings a new challenge. How can a neural network model dependencies between pieces of information that are separated in time? LSTMs did not appear out of nowhere. Before LSTMs, there were recurrent neural networks, or RNNs. These were developed across several works in the late 1980s. Traditional RNNs aren't the main focus of this video, but we need some context of what these are in order to understand what problems LSTMs are solving. A feed-forward neural network moves information in one direction, starting at the input and moving towards the output, but it doesn't retain any of that information once the computation is done. RNNs do that by adding something new, feedback loops. Instead of only sending neural activity forward, a recurrent neural network can feed activity back into itself, meaning the internal state of the network depends not just on the input, but also the previous states of the network. So, the network is kind of carrying along this evolving internal context, a state that persists across time. So, for something like our sentence at the beginning, I grew up in France, I speak fluent blank, as the network processes each word, it also carries forward information from previous time steps. By the time we get to the word fluent, we want the network's internal state to still have some information representing grew up in France. And because of this, RNNs became a natural architecture for sequence learning. Language, music, time series, or any setting where previous information might matter later. So, instead of processing a sequence as a bunch of unrelated inputs, RNNs carry previous context forward through time. So, already before LSTMs, the basic idea behind sequence learning was there. But I haven't mentioned the big problem with RNNs at the time. RNNs, in theory, could preserve information through time, but in practice, they were extremely difficult to train when information needed to persist through long spans of time. And to see why, we need to briefly cover how RNNs learn. We established in the last video that the primary method of training neural networks was backpropagation. Let the network run, measure how wrong it is at the output, then propagate the error backward so the network can adjust its weights and reduce error. With an RNN, the network is not just spread across layers, but it's also spread across time. So when you propagate error backwards, it has to travel through many previous time steps. So, if the error depends on something that happened many time steps ago, the error signal has to be carried back all the way through those earlier steps. And this is where the problem shows up. As these error signals, or more precisely, the gradients, flow backward through time, they tend to either vanish, meaning becoming extremely small, close to zero, or explode, meaning growing uncontrollably large. The most famous version of this issue is known as the vanishing gradient problem. So, even if the network can store information through long periods of time, it could still fail to learn what information matters, since the learning signal fades away before it reaches the relevant moment. So, we end up with a weird situation, where RNNs can remember things in principle, but they cannot learn what they're supposed to remember. The authors of the LSTM paper treat this as an architectural problem. They argue in a standard RNN, the hidden state tries to do too many things at once. It has to represent the current computation, carry previous information, transform that information, and also support learning signals over long timescales. All of these behaviors are expected from one single mechanism. To address the problem, the authors propose to separate these responsibilities, separating memory from current computation and introducing mechanisms to control this memory. Now that we have this context, we can dive into the paper to see how the authors did this. The authors redesigned the architecture of an RNN around one central goal, creating a path through the network where information can persist over time, but also where the error signal can persist over time. LSTMs are still recurrent neural networks, processing sequences step by step and carrying internal state forward through time. But inside this recurrent structure, LSTMs have something new, a specialized memory mechanism. The paper calls this core mechanism a memory cell. The memory cell is not just a normal network unit. It's a small architectural module inside the recurrent network, kind of like a tiny root. And if we want this memory cell to persist in internal state, a natural move is to give it a self-connection, so its internal state can be carried from one time step to the next. If nothing interferes with it, the state can simply keep persisting. The authors call this internal pathway the constant error carousel, or CEC. So the CEC is designed so that the state can persist through time, but it also makes it much easier for the error signal to reach far back into the past. This helps solve the vanishing gradient problem we mentioned earlier, but we'll get into this later in the video. Already, this memory cell is an improvement over traditional RNNs, because now the network has a place specifically designed to store information through time. But this naive memory still does not solve the problem of control. Suppose the network is reading a sequence similar to what we saw at the beginning of the video. I grew up in France. I spent many years abroad. I still speak fluent blank. And let's just assume for now, early in processing, the memory cell stored an internal state related to France. Now imagine what happens as the sequence continues. Let's say we're on the word spent. What should happen in the memory cell now? Should this spent internal state overwrite the previously stored France internal state? Should we just ignore the word entirely? If every new input can freely modify memory, then the important information is going to get drowned out by new inputs, and the whole problem of modeling long-term dependencies becomes impossible. This is where the authors introduce the first control mechanism, the input gate. The input gate is attached to the memory cell, and it controls whether new information is allowed to enter the cell and modify its internal state. So now, when the network reaches the word spent, the input gate can say, this new input is not something that should be stored in the memory cell right now. This memory cell can persist the France state, while the rest of the network continues processing the sentence. If the memory cell is like a tiny little room, then the input gate is a doorman who allows what goes into that room. So the input gate solves a specific problem. It lets the network distinguish when it should write to memory and when it should just preserve what's already there. Now, we have a dedicated place for memory and a dedicated mechanism for deciding when this memory should be written to. But there's another problem. Let's go back to the example. Now the network can process more words without destroying the memory of France and carry this memory forward. If we move down the sequence many years abroad, should this memory of France influence the network's computation at every single step? Probably not. It may be important overall, but not equally relevant at every moment. What really matters is that when the network reaches the blank at the end, I still speak fluent blank, the stored memory can become available and influence the computation. So, the second problem is also a control problem. If stored information is always exposed, then the memory could just be disruptive noise. And if it's always suppressed, then storing it would be useless. This motivates the second control mechanism, the output gate. The output gate controls whether the contents of the memory cell are allowed to influence the rest of the network at the current time step. So now, the memory cell is not just storing information selectively, it's also retrieving information selectively. Again, thinking of our memory cell as a room, with the input gate as a doorman controlling what goes in, the output gate is another doorman, controlling what comes out. So, while the input gate decides when the network writes to memory, the output gate decides when the network reads from memory. So, the architectural improvement over a plain RNN is clear. A standard RNN has one hidden state trying to do everything at once. But LSTMs introduce the memory cell, a small structured module with these three distinct mechanisms: the persistent internal state, the CEC, controlled updates to the state, the input gate, and controlled outputs from the state, the output gate. But how do these gates actually know when to open and close? Like everything else in a neural network, it simply learns this through training. This is the beauty of error-driven learning. The gates are not hand-programmed rules, but their behavior is learned through error-driven adjustment. If this idea still confuses you, make sure you've seen the last video in the series. I'll link it in the top right. But we're still left with a hanging question. How does this new architecture actually enable the learning of long-term dependencies, solving the problem we mentioned earlier? And the answer starts with diving into the vanishing gradient problem in ordinary RNNs. When an ordinary RNN makes a prediction at the end of a sequence, and that prediction depends on something that happened much earlier, the learning signal has to travel backwards through all of the time steps in between. A useful way to picture this is passing a signal through a long chain of transformations. At each time step, the hidden state gets transformed, and then at the next time step, this new state gets transformed, and then again, and again. So, when we send error backward through time, we're effectively unwinding that whole chain. And the issue arises because every step in that chain tends to scale the error by some amount. So, moving backwards through each time step either scales the error signal down or scales it up. And when the scaling happens repeatedly over many time steps, small effects compound very quickly, making the gradient either vanish or explode. So, the vanishing gradient problem is a structural consequence of repeatedly transforming the hidden state through time. So, to make long-range learning easier, we need to create a path through time where this repeated scaling does not happen, or at least does not compound exponentially. And this is the job of the constant error carousel. We mentioned that the internal state of the memory cell is self-connected. So the state is simply carried forward from one time step to the next, instead of being repeatedly transformed. Inside the LSTM memory cell, there's a more stable path. The internal state is carried forward and only modified at select times, when the control mechanisms decide it should be. This gives the error a route backwards that's less vulnerable to the repeated transformations that make long-range learning unstable in ordinary RNNs. And the authors pair this architecture with a particular training treatment, because once you've built this protected path for error, you want the error to make use of this pathway. The basic idea is that when error is propagated backwards, error is allowed to flow freely through the internal state of the memory cell where the path is stable. But when the error tries to spread backwards through all the other recurrent routes in the usual way, the authors cut that propagation off, so the error doesn't stray off into unstable pathways. So, the contribution of the paper is really these two things working together: a recurrent architecture with a dedicated memory path, and a learning procedure that preserves long-range error flow by enabling use of that pathway. And following this, the broader significance is clear. LSTMs are a neural architecture organized and trained in such a way that long-range temporal relationships can be learned. So, what did LSTMs actually add to the story of AI architecture? Neural networks already had memory, at least in principle. LSTMs introduced controlled persistent memory, hence the name long short-term memory. LSTMs create a place where memory can persist. The architecture regulates when information is updated, and it regulates when that information matters for the current computation. And, because the pathway for this information is stable, it becomes much easier for learning to connect something happening now with something that happened much earlier. LSTMs became a major step forward in sequence learning, especially as later work applied them to real-world domains like language, handwriting, speech, music, time series, any domain where the significance of what you see now depends on something that happened previously. Though, the paper really only tests experiments on specific tasks that typical RNNs struggle with, for example, delayed signal recall. But LSTMs are also philosophically pretty interesting. Sequence learning, something inherently fundamental to human cognition, is not just about memory, but about memory under control. It's not enough for a system to have internal states, it has to regulate them. It has to decide what deserves persistence. This shows us memory is active, selective, and entangled with representation itself. To remember something is already to represent the world in a certain way. So, LSTMs operate through this evolving internal memory. But us humans don't rely on just internal memory. We also rely on other things, like representations outside ourselves that carry information for us. And language is one of the clearest examples of that. Words and sentences let us package up meaning into stable forms that can be reused, communicated, and recombined. So not every thought has to be built from scratch or explicitly stored somewhere in our brains. If words are the external carriers of so much human knowledge, how should a neural network represent them internally in a way where similarity and context are built into the representation itself? In my next video, we'll talk about the paper A Neural Probabilistic Language Model, where this idea becomes central. This paper gets into the problem of language modeling, and this is really where we start to see how AI evolved into what it is today. Thanks for watching. See you guys in the next one.